Hi everyone. Today let's talk about sessions 11.2, properties of combinatorial circuits. So here are some properties of combinatorial circuits. For all A, B, C in the set containing the two numbers 0 and 1, so those are the bits, right? We have the associative law. So that means A or B or C equals A, or we can calculate B or C first. Or we can calculate A and B first, and then when we calculate and C, or we can calculate B and C first, and then we use it to and C and A, okay? This is the associative laws, okay? And next, we have the commutative laws. A and B equals B and A, and A or B equals B or A. Okay, so the AND operator and OR operator, they're commutative. Okay, and associative. So when we see the two operators together, we have the distributive law. So A and B or C equals A and B or A and C. Okay, we use the parentheses to denote the order we want to calculate. Okay. And then A or B and C equals A or B and A or C. Okay, that's the distributive law. We also have the identity law. A and 1 is A. Okay, so it's like 0 and 1 is 0, 1 and 1 is 1. So that's why A and 1 is A. A or 0 is A. So 1 or 0 is 1, 0 or 0 is 0. So that's why A or 0 is A. And we have the complement laws. A or not A is 1. A and not A is 0. So far, so good, everybody? Okay, so the properties list above holds for a variety of systems. Any system satisfying these properties is called a Boolean algebra. So now we know combinatorial circuits is a Boolean algebra. Actually, the set we learned about before is also a Boolean algebra. Okay, for the sets, we have union, we have intersection, we have complement, right? And the 0 plays a role as like the empty set. The 1 plays role as the universal set. Okay? Alright, let's continue. Definition. Let x1 be, so this capital X, they are like the expressions. We have x1, x2, xn, and x2 is like a function of the variables x1, x2, xn. Then we say x1 equals x2. Okay. They are equal if x1 of the variables equals x2 of the variables for all the xi, where xi is the elements of the bits 0 and 1. So Z2 is the set of the two elements 0 and 1. So which means if we have the same inputs, then we should have the same outputs. Okay, next we say two combinatorial circuits, each having inputs x1, x2, xn are equivalent if whenever the circuits receive the same inputs, they produce the same outputs. Okay, so for the Boolean expressions, we say they are equal, but for the combinatorial circuits, we say they are equivalent. Okay. And next theorem, let C1 and C2 be combinatorial circuits represented by the Boolean expressions x1 and x2. Then C1 and C2 are equivalent if and only if x1 equals x2. So far, so good, everybody. Let's look at some example. So here we have x and y. So let's calculate the table for x bar or y. So y, you can see that because this is the OR, if y is 1, whatever whatever or 1 is gonna be 1. So if y is 1 right here, so we get 0. And for the rest, we have x bar is 0, 0 or 0 is 0 here. 1 bar is 1, 1 or 0 is 1. So far so good, everybody. Next, we have x bar. So 0 and 0 is 0. Here we have 0 and 1 is 0. Okay, 0 and 1 is 0. And then here we have 1 and 0 is 0. Here we have 1 and 1 is 1. Oh, do you see those two set of values are the same? And what do we say? We say those two Boolean expressions are equal. So x bar or y equals x bar and y bar. Okay. You might have a question. Do we see something similar before? I want to remind you the De Morgan's law. Okay. De Morgan's law, x bar and y bar equals, we distribute it, this is x, this is or. Okay, so yeah, actually 3 of them are equal, okay? And you can see this guy and this guy, they're different, but they are equal. All right, let's continue. Okay, so let's look at these two combinatorial circuits. And actually, the first one, this guy corresponds to or, this is not. So this is A or B, and then we have not. So far, so good. Well, this guy is, let's see. And here we have A, B, because those are not, and here we have and. So A bar and B bar. Ooh, see? This is actually the De Morgan's law, right? And you can see here, if A and B are 1, so 1, 1, or give us 1, and then not give us 0. And then next, 1 or 0 is 1, not 1, 0, 0, 1, give us 1, not 1, 0, and then 0, 0, 0 or 0, 1 is 0, and then not 0 is 1, okay? So this is how we get the logic tables. Second one, this guy will give us 0 and 0, give us 0. And actually, as long as one of them is 0, we get 0. So this guy, not 1 is 0, we also get 0. So if both of them are 1, if both of them are 0, the bar, A bar and B bar is going to be 1. 1 and 1 is 1. So far, so good, everybody. And you can see the values are the same. So we say those two circuits are equivalent. And then for the Boolean expression, this guy equals this guy. This is actually the De Morgan's law, right? Okay, let's continue. Alright, to show that two circuits are equivalent, we just need to show when given the same input, the circuits produce the same outputs. Okay, and we can do this with the logic table. Alright, here we have more examples. First of all, let's figure out, okay, so this is not gay, this is or, this is not, this is or. Sorry, and then this is and, this is not. This is not, this is or, this is and. So far, so good, everybody. Okay, now let's change this. Let's call this is A. Let's call this B. Let's figure out the outputs. Okay. So, let's see. Okay. All right. So let's look at the first path. You see, If x1 is 1 or 1 will give us 1, but not 1 give us 0, then 0 or something. It depends on the other one. Okay, let's really check on each of them. So if we have 1 1 1 1 1 1, then not 1 is 0, 1 or 0 is 1, not 1 is 0, and the other one, not 1 is 0, 0 and 1 is 0, 0 or 0 give us 0. Okay, next 1 1 0. If this is 0, how would that change? So 0 and 0 is still 0. We still have the same result, right? 1 0 1. So 1 0 1 1. So not so this is still 1, and this is 0 0. Okay, and then how about this guy? This is 0 1 and 0 is 0. They still have the same result. So far so good. Okay, next 1 0 0. And 0 and 0 0. This is still 1. Oh, it's still the same result. Okay, is everybody following? So remember, you can pause the video at any time, and then you can think more. So x1 next, x1 0 1 1 0 1 1. So 0 and then not 1 is 0, 0 or 0 0, not 0 1. Ooh, 1 or whatever is gonna be 1. Okay, so in fact, if x1 is 0, x2 is 1, then the result is gonna be 1. Okay, so next 0 1, now 0 is 1, then this guy will give us 1, not 1 is 0. Here, not 0 give us 1, 1 and 1 is 1. Oh, 1 or 0 is 1. Alright, finally 0 0 0. Oh, so 1 and 0 will give us 0, 0 or 0 is 0. So far so good, everybody? Okay, let me erase everything here. Okay, so this is how we come up with the logic table. Let's look at the other graph. The other graph is easier. So if x is 1, not 1 is 0. Oh, yeah, 0 and whatever is 0. Okay, so as long as x is 1, then all of these will give us zeros. That's easy, okay? And when x1 is 0, not 0 is 1, but 1 and whatever, it depends on the other path. So let's look at x2. Oops. x2 and x3. So if x2 and x3 are both 1, 1 or 1 is 1, 1 and 1 is 1. Oh, you see, if x2 and x3, one of them is 1, the result is going to be 1, then 1 and 1 is 1. Okay? And then finally, if both of them are 0, 0 or 0, 0, 0 and 1 is 0. Okay, so now we have figured out the logic tables, and you can see they are the same. So we can say those two combinatorial circuits are equivalent. Okay, circuits are equivalent. Okay. Alright, let's continue. So right now you can pause the video and try to work on this problem. Have you done? Yes. Let's check. So let's see. This is and this is or, this is or, this is and. So this guy, if 1 1, 1 and 1 is 1, 1 or 1 is 1. Right? And 1 0, 1 and 0 0, 0 or 0 is 0. So far, so good. Next, 0, 1. 0 and 1 is 0. Oh, sorry. The previous, I think I look at it wrong. So it is 1, 0, and then this is 0. But the 0, we're looking at the x1. So or x1 is 1. So 0 or 1 is 1. Okay. Now if we have 0, 1, this is 0, but we look at the first one is 0 is 0 or 0 is 0. And when both of them are 0 and 0, and then this guy is also 0, we have 0. So far, so good. So sometimes it's very important to check our work because we might make mistakes. Next, 1, 1, 1 or 1 is 1, 1. So this is 1 and 1 is 1. Then let's see, 1, 0. 1 or 1, 0 is 1, 1 and 1 is also 1. Next, 0, 1. 0 or 1 is 1. And then this is 0. So 1 and 0 is 0. 0, 0, 0 or 0, 0, 0 and 0 is 0. Oh, they're also the same. Then we say those combinatorial circuits are equivalent. So far, so good, everybody. All right, let's continue. Oh, that's it for sessions 11.2. So, yeah, we talk about the properties of combinatorial circuits. We defined Boolean algebra. And then we also talk about when our two Boolean expressions are equal and when are the two combinatorial circuits are equivalent. Okay, we check the logic tables for all combinations of the inputs. We make sure they have the set of the outputs, then the circuits are equivalent. All right, that's it for today. Have a nice day. Bye.